Okay, so themes and layers, I'm repeating for the camera because I'm recording now. Themes and layers is about the fact that we can separate layers or data into layers. So the diagram you see on board tells you that for the same location of longitude 35, 45, 20, and then longitude 121, 28, same coordinate, you can have several layers. You can have soil type, you can have even constituency is one layer, since you are voting tomorrow. You can have lithology, you can have geology, you can have um, different topics for the same place. Are you with me? All right. So what a place means to someone doesn't mean the same to you. Are you with me? If you are building, like I said, the building itself has its own layers. Are you okay? First floor, second floor plan, third floor plan. Talk about plumbing, electrical. All these are different layers. So we can group our ideas in terms of data. In terms of data, we can group our ideas. All right. So GIS allows us to separate data into different themes on purpose. Is that okay? And I always keep saying that once you are separating, then you should get ready to recombine. Are you okay? So now we talk about map overlay. So I've just talked about the layers, and now the overlay is a combination. It's all right. Now we can do what we call an overlay operation. In the overlay operation, then we can actually, combine all the layers in interesting ways. And that's why you are looking on the board. We can bring them all together and have what we call the union overlay. Okay, so I can bring two data sets together and just add them one on top of the other and then fuse them. I can actually take two layers and just find the intersection between the two layers. Is that okay? So I find the two inputs and then I retain the overlap region. And so we have what we call the intersect overlay. You can have the symmetric difference, okay, overlay, in which case I take the intersection area and I say, I don't want that. I want anything apart from the intersection area. So I only keep the overlap. I don't keep the overlap area. I keep that one apart. So you get something like, an island, okay, some kind of hole, okay. All right. So that is the map overlay for you. Let me just go back to the board and see if I can illustrate any further. Okay. So when you look at what I have on the board, this is a first layer, and then that's the second layer I'm bringing on top. So for the same location, I'm having two layers. Okay, so on the first layer, I can decide that I'm capturing pipelines. So that's a pipeline. Let's assume that's a pipeline. Then I can decide that, okay, in the bottom layer, I'm keeping just, say, constituencies. Okay, so this one constituency. So for your pipeline project, you can see that you have one layer, you are putting on one layer, and then on the other layer, you have the constituency. So what you can do is that you can combine the two layers and then have a combination of constituency and then pipeline network. Okay. So all of them will be together. So I just withdraw this. Then I put my pipeline on top. Okay. So now it will be looking something like that. So this is a union overlay. Okay. They are combined. Okay. Now, what if we actually make maybe this is a West African pipeline project. So it's big enough. Okay. So we can now have something like that. So you can see that it's not all the constituency or all parts of this constituency, the two constituencies that are going to be affected. So one constituency is some parts of a particular constituency is going to be affected by the pipeline project, and then some parts won't be. So that is the idea of doing what we call the intersect overlay. In that case, this area is kept, okay, which is the overlapping area. Okay. So that can be extracted. Okay, so once we undertake an overlay operation, we get the opportunity to also do an extraction. Okay, what it means is that we can take all the routes in Ghana and then just extract just the routes for Accra routes, only the Accra routes, using what? The intersect. Is that okay? Now the intersect, it looks more like And the union looks more like, remember this set theory thing, A union B. So this is looking more like A union B. This is looking like A intersection B. Is that okay? Don't go and write this in exam. I'm only, explaining something to you. So the intersection, remember we used to do that, two circles, yeah, and then you shade that, all right, two circles, and you shade everything. That is what is happening. It looks more like that. Are you okay? All right. So let's go back to the lecture. All right. So the symmetric difference, instead of keeping the intersection area, it will rather leave that. I don't want that, and then it will take everything outside it. Is that okay? So they all have purposes, and they can be used as appropriate. Any question on this? Overlay, basically, this is all I want you to know. As construction students learning GIS. Yeah, there's so much we can learn, but this is so far what I want you to know. And that's what you need to know, in fact, for overlay operations and layers and themes. All right. No question means I change topic and I talk about something else. So let's move on. Okay, so here you can see, I'm trying to explain further. Combination of different layers. This is the first layer. This is the second one. Okay, and then this is the union overlay. All right, over here there's a project. Okay, so you can see that that's that kind of, I don't know what it is, could be a tunnel or something running through. All right, and then we want to find out which concessions. You see the way they are looking rectangular, they look more like some minor concession there. We want to find out how they affect IOK or whatever. It depends on what the problem is that you are trying to solve using these overlays. And so there you go. And then obviously we are trying to say that the computer can tell you exactly which record. So remember that the GIS, when we start doing a practical, you appreciate that everything we are showing, it goes into a table, as I talked about earlier on. So all your buildings are being kept in a tabular form, so in a kind of database. Yeah, look at it in terms of the database definition of GIS. You can look at GIS like it's a database. All right, so this is the symmetric difference. So in that case, we are not interested in this area. We are interested in this area. So it's like A intersection B complements. Okay, that is what you are looking at. Then you put some kind of where is it? If you still remember your set theory, you can relate to what I'm talking about. Is okay. All right, so that is it for the overlay, and we're saying that we can do that to extract data. Is okay. All right, a GIS process similar to vector overlay, though it can be used. We can use, overlay is only for vector GIS. Later we'll find out that vector is what we are talking about. Once we're talking about polygons, we're dealing with vector. All right, but it can be used in pictures as well. Is that okay? There's a lot we can do. Okay, so yeah, like I said, data extraction involves clipping. We can clip data. You take one layer, bring it on top of another one, then you just cut it. Are you okay? All right, it's like a cookie cutter thingy. All right, we can make it what we call the map algebra. So that is used for the raster, but later we don't even know what raster is. So we talk about raster in ensuing lectures coming up. Talk about that. All right, great. If you don't have a question, then the next topic is actually waiting for us here. You can talk about buffer operations. It's good to ask questions because when you get overwhelmed with a lot of information, the best way to put it in a certain way, orderly way, is to ask questions, please. So remember that I'm moving quite fast. Is that okay? All right, great. Next topic is buffer operations. Buffer operations. So what is a buffer, or what is buffering? So buffering is used to constrain space around individual land features. Okay, so we have a land feature or a geographic feature, and we want to constrain the space around it. Is that okay? So when we're able to do that, we have what we call a buffer. Okay, That we call a buffer. Okay, so my marker doesn't always work when I don't know, when I'm teaching. I don't get it to be working. Okay, but then let's move
Hello,
on.
sir.
Yes, do you have a question?
Yeah, the buffer. Can you please throw more light on?
I just started, please. I just started, so
Okay.
I haven't thrown any light on it yet. Okay,
Okay.
all right. So let me talk about it. So that is why I've come here. I'm here because I want to explain the buffer more to you. All right, but my marker isn't working well. How do you constrain space around this dot? You see a dot I've put here. Okay. So the English word is constrain. Constrain. What does constrain? Another word for constrain. To constrain something is to keep it, to keep. Are you okay? So okay, restrain is also there. Are you okay? To restrain a child. That means don't let the child move. Constrain.
Or to limit.
Limit. Thank you very much. So how do we limit space around this point? You know, who can tell me? How do you limit space around? So I want you have a kid standing here, and you want to tell the kid that they shouldn't, you know, you want to limit the space within which the kid can play. So you have a child, and you want to constrain space around the child, the location of the child. How would you do it practically? I want the class to talk now. I want your views on it. So let me hear from you. Switch on your microphone and then contribute. How do you constrain
Sir,
space? You have a little child and you want to constrain the space around where the child is. How do you do it? How do you implement that?
you set a boundary around it.
You set a boundary. So I want you to go there and set the boundary. How do you set the boundary?
Come
So
again.
are you going to use?
Come again. The question.
The question is that you have a child or a kid who is actually located at this point. The dot, the black dot, which now I've put some red in there. How do you constrain the space around so that the child doesn't go beyond? Please, if you're not contributing to the class, mute your mic. It's just gentlemanly to do that. Mute your mic if you're not contributing to the class. Or after talking, mute your mic. All right. So how do you constrain the space around where the child is so that the child doesn't play beyond certain space? How do you constrain the space? Please, the person who is talking, I'm about to take you out. I'm taking you out of the class. It's possible. You don't know that. Okay. So how do you constrain the space around where the child is? When you are ready to talk, or mute your mic, because some of you you don't know how to control your mic. How would you do that? Someone says that create a boundary. How do you create a boundary? Tell us. How do you create that boundary?
What I'm trying to say is,
yeah, you have to be specific, please. What we want you to do is that tell us exactly how you do it. So don't give us an idea. Tell us exactly how you do it so that I can use it to explain the buffering to you. Yeah. How would you do it?
You build a wall.
You will build a wall. Okay.
Yes.
Okay. So you build a wall this way.
So maybe 2 centimeters.
No, for the.
So like you fence it like 2 centimeters.
Okay, so this is 2 centimeters.
Yes. Yeah, you fence the whole area.
So you
for
do
the 4 corners.
Yes.
Exactly.
Yes.
You do something like this.
Yes.
Yes, sir.
Okay, not a bad idea, but that's not the best way to do it. Do you know why? Because
no, sir.
You want to actually limit the child by a certain distance. The quickest way to do that is to define one value, not too many values. Because remember that this distance here it's not the same as this one. Even in the case of, I think when you have a cube, no, a square rather, okay, you realize that you have a challenge. Even though it seems to be like not a bad idea though, but you always have, you know, a certain moving from here to here. It's not the same as moving from here to here. You agree?
Yes, sir.
Okay, so you have to provide how many values to define the constraints? About 2, isn't it? 2 parameters, right? Let's assume you are instructing someone to construct this. You need 2 values, right? You have to first
Yes,
find
sir.
the child, isn't it? But then the child will now be moving, not always within a certain limit of 2 centimeters. Sometimes you go a little beyond 2 centimeters. Are you with me? All right, but I think you get the idea. That is exactly how, you know, buffering works. You simply have to define an area. So the quickest way to define the region, constraint space around a point, is to make use of what? A circular polygon. So you take the point and then you draw a circle around it. Okay, so I don't know if my pen writes. My pen isn't writing. Okay, so I'll draw a circle. Okay, and by doing that, I now have one value because every circle has just one radii. Are you okay? So we can always say that we are restraining you by a certain distance, say 2 kilometers or whatever it is. Are you okay? Or 2 centimeters, as you said. 2 centimeters is not realistic, obviously. Yeah, see 22 centimeters. This being that's not realistic. 220 centimeters. Are you okay? But that is,
Yes, sir.
this is how you actually create what we call a circular buffer. Circular, sorry, I can't write well with this. Are you okay? I'm using the mouse. I'm supposed to use my touch screen, but it's not helping me. It always goes off. All right, so this is a circular buffer. And then you can also have, you know, in the case when you have a line, how do you handle that one? When you have a line, how do you restrain space around the line? Anybody? When you have a line, how do I constrain the space around the line? So that if someone is moving, you know, along the line, there's a certain limit. Are you okay? If you've done some, it's a coordinate geometry or something like that, it's a certain topic in maths where we talk about the locus of a point. That is what we are describing here. Are you okay? All right, so to constrain space around the line, you have to offset, draw a parallel line, and then you cannot draw a semi-circle to cap it. Okay, now in the case of the point buffer, you get a circular polygon and the area is defined by that. The polygon this way, all those areas are the buffer, that's the buffer zone. And for the line, this is the buffer zone. Okay, so the radius of the semicircle is going to be the buffer, is the so-called buffer distance. Well, so-called, I like using that phrase. It's the buffer distance. Buffer distance. So the buffer distance in this case is 220 centimeters. Okay. Distance. Okay, and then the buffer distance in this case will be a value here. Let's call it M. Okay, so that same distance will be the distance from here to here. For the offsets, okay, so here to here will be M. Here to here will be M. Are you getting that? And then we now create a polygon. So the result of every buffer operation or buffering is a polygon. Okay, you get a polygon. This one is called a point buffering. So when you buffer around a point, create a point buffer. So this one is a line buffer. So you can imagine the last one that I'm going to talk about is going to be what? Polygon or polygonal buffer. Polygon. Writing with this is not easy. Buffer. Polygonal buffer. Whatever we call it. In that case, you have a polygon and you want to create a buffer around it. So you offset it by a certain distance all around it. Oops, okay. I think my software here that I'm using for the presentation is trying to show me that. Okay, so this is what you have. Okay, so the distance, the buffer distance is now a set constant value, a certain constant value. All right, except that GIS keeps so many features that every feature can be buffered per a certain attribute. Okay, so you can store, say, a certain value inside the database, the geodatabase, as we call it, and then we offset. So if you get a certain building, okay, the buffer distance will be different from, another one. So you take this building will have a different buffer distance from this, based on what we've put inside the software. We'll be having different buffer distances. Okay, but at the end of the day, a buffer is area, a buffer polygon is created. So this is the buffer. Okay. All right. So for polygons, you can have what we call the inner and outer buffer. What we have here, up here, is the outer buffer. Outer buffer. Okay, but you can also have an inner buffer. Inner buffer. I'll tell you when and when you use what. Okay, so the inner buffer works this way. You have the polygon, all right. Okay, but then instead of you to do it outside, you do it inside. You offset. Normally these lines are parallel to each other. Okay, so we are reconstructing this whole thing by offsetting a distance from the original object. So now the buffer zone then becomes what? An inner one. So we get an area. We always have to get an area. So the offset is actually from here to here. Okay. All right. When do we use the inner buffer? When do you use the outer buffer? It depends on what you are doing and what you are trying to do. We look at something like a fire belt. Okay. Or if you're working on a project in which you have to make sure that water is surrounding the whole thing. Okay. But then you need to a certain distance. So let's use a fire belt example. It will be very easy to understand. Fire belts are created by farmers to prevent their farms getting gutted. So they weed around the farm. All right. But should the farmer implement an inner or an outer buffer? That's the question. Okay. Should I implement an inner or an outer buffer? Okay, so if you are doing an inner buffer, you are cutting within your own farm boundary. Okay, if you are doing an outer buffer, more or less you are cutting outside your farm. So you can see that you don't want to do an outer buffer, but you want to rather do what? An inner buffer for a fire belt. Okay. All right. So that is polygonal buffer, inner and outer buffer. In most software, in QGIS, for example, you put in a negative value for the buffer distance and you get an inner buffer. So I think we'll try that in our tutorial. Okay. Meanwhile, let's go back and see if we've actually tagged and everything. So buffering, that is everything that I've talked about. I don't think there's nothing more that I haven't talked about. Yes, it's generally used for defining all the spaces within a certain distance of a type of feature. All the things you are looking at on the board, these are circular, buffers. Yeah, circular polygon, a point buffer, giving us a circular polygon. These are linear or line buffers. Are you okay? And then we can have a polygonal linear buffer, if you like, polygonal buffer. You have a polygon and you want to buffer it. So there's a distance that has been, created. You can see from here to here. That is the same as from here to here. That is the buffer distance. Is that okay? So this is possibly an outer buffer if the yellow area is the original object, the original feature. So we don't say object, we say feature. All right, geographical feature. All right, or land feature, whichever way you look at it. Yes. So there you go. We can also buffer pixels. I told you that we have the pictures and then we have the line points polygon. You have the raster, you have the vector. We'll talk about it again. You understand it better as we go. So buffering points create circular polygons, and the radius of the circular polygon is called the buffer distance. I think we talked about that. I've touched on that already. This is a linear polygon, okay, a line polygon. Okay. Okay, so there you go. When you buffer lines, we offset or we create parallel lines to the line. Okay, and then we cap the bounds. We cap the bounds. So we create two parallel lines, then you join them up with a cap. All right, and that's it. We're done. Okay, so more examples of buffer operations or buffering. I think we've seen this already. All right, buffering of polygonal surface uses most of the same concepts used for line buffering. The only significant change is that the polygon buffer is created on only one side of the line that defines a polygon. Is that okay? All right. So in buffering a line, we do both sides of the line. In buffering a polygon, we do only one side. That's what we are saying over here. Applications is in wireless coverage. For example, if you are providing Wi-Fi, so the internet cafes, they can use this, but they probably wouldn't know. Is that okay? And they won't call me because I'll charge them very well. On a funny note, but you realize that to know if the people in the area are receiving the wireless signal, you first have to look at the manufacturer's, documents, the documentation that came along with the device. Look at how far the signals can travel. Okay, you mount the signal out there. You get to know your area. Get a map for the area. Okay, so the basic thing you can do is just draw a circle around where your cafe is, and then you will know all the houses that will be reached. That's like a simple point buffer. Are you okay? All right. So you can do so many of them if you have several points, are you okay, of transmission of the signal. Are you okay? And then there you go. You've solved the problem. You've gotten to know that someone will receive your signal. So you know where to go and advertise. You know where to go and talk to, which people to go and talk to about your internet cafe. Are you okay? All right. Instead of you pasting your way everywhere, nobody, you're just wasting paper. All right. So that is the idea of that. So we can use buffers for house arrest. If the court orders someone that you've been, house arrest, you're under house arrest, don't move from your house 2 kilometers away, you shouldn't be seen. You can be arrested at the wrong place, at the right place. You'll be 2 kilometers away, but you'll be arrested because the court and the law enforcers haven't really applied some buffering here. And here they have to also apply the concept of layers, because first they have to, first get the layer. Are you okay? You get to know the circular polygon around your house. Take 2 kilometers, okay? Reduce it by the map scale. We talk about map scale later on. And then now we overlay and find out which street that you were caught on. You need a street layer. And then we find exactly the intersection between the boundaries of the circular polygon and the streets. Are you okay? Then we can say, okay, you went beyond your, restraints. They have what they call ASBO in the UK, antisocial behavior order. They will be applied. This is how they'll be implemented. Is that okay? All right. Anyway, don't go and say you're an expert. Just call me and I'll take the job. Anyway, so yeah, because there could be more to it than you think. That's the truth. We like that too much. Anyway, that's the end of today's lecture. And you have a question you can ask. So I'm giving you a few seconds. because obviously the Zoom is even ending in a few minutes. But if you have a question on the topics that we have tagged on today, you can ask. Otherwise, then we are ending the lecture. If you have a question, put up your hand, unmute yourself, ask a question. If you don't, one day I'll ask you a question, and don't say that wasn't fair. Is that okay? Yes. All right. Any question?
Hello, sir.
Hello, GW.
Yeah. Yes, sir. So
Why
I
are you
want to find out
GW?
because
Mm.
that is George William.
Okay, George Williams. Okay, that's nice.
George, yeah.
Okay, great. I have to take attendance.
I want to find out because what is going on? I've realized that you are talking about areas, you are talking about coordinates.
Yes.
Are we in future going to deal with calculations?
Let me talk about in future, as in this class.
Yes, as we go on, are we very soon, introduce calculation?
Into what we are talking about.
Yes, please. You know, the coordinates
I
is
think
figures.
Of course, there will
George.
be some calculations.
But why are you answering, Richard?
Yes, sir.
Are you the lecturer? Please.
So where?
No. Please be serious. Serious. So GW. Don't mind Richard. Don't mind him. The thing is,
Okay, sir.
yes, there are different levels. You are learning GIS. This is the
Okay.
principles. Remember that. And so
Okay.
it's the beginning of something bigger.
Okay.
So per this class,
Oh, okay.
there's a scoop. There's a scoop. I can't teach you everything in GIS. Are you with me?
Oh, okay.
Yeah, so don't after learning this course, don't go and start writing proposals, that you are going to take GIS. You just gotten to understand the principles. Are you okay?
Okay, sir. Okay,
So you
sir.
can probably go and take a
Thank you
master's in
very much.
GIS. That's fine. You learn more, there'll be more calculations. But obviously in this class, there will be calculations, but I don't think they will be what we call calculations. No, I don't think so. I teach engineering
Oh, okay.
students, but I
Okay.
don't think that's what we'll be doing here. But it means you are afraid of calculations. I was expecting that you asked a question about what I taught you. So your question is rather if the course is going to be
No,
difficult.
no,
I don't like
no,
questions like
no,
that. I'll be
no.
honest with you. Yes. The question has to be
No,
about
no,
what you've
no,
been taught,
sir.
not, okay, sir, is this course going to be difficult? No, don't be asking questions like that. Yeah. Yes.
Thank you, sir.
Your question is like, is this going to be a very complicated something? Yes, it's going to be very complicated. Yeah.
Okay, sir. Okay, sir.
Okay.
Maybe I should
All
have
right.
put it this way.
No, but I actually want questions on what I've taught you, because if you've understood me too, I think you can contribute. It also helps. But most of the time, you are not the first person to do that. You teach, you finish. The question is, say, so are you going to give us a handout? What it means is that you've understood everything I talked about. But the funny thing is that I want you to ask questions so that when I ask you a question, you can answer it. Because some of the questions you are asking these days, they are very analytical, they are evaluating, they are quite challenging. Are you okay? They require you to do critical analysis. So class, this is the opportunity to ask me a question. We won't go back talk about topology again. We won't go back and talk about themes and layers. But it also means that you've really understood me. That's another thing. But most of the time, the class hasn't really understood what was said. So, but anyway. So if we don't have any question, about what are the topics that have been tagged on today, which is metadata, overlay, topology, and we've just ended on buffering. So these are concepts in GIS that are used to solve problems. If you don't have any question on these, I guess we will
Okay,
end.
sir.
This.
Sir.
Yes.
For the map overlay.
Yes.
The one you talk about, the map overlay. You know, you need you use a sketch like the 1 and then the 2.
Yes.
And then out of it, we were able to get the union overlay.
That's right.
So does it mean we can also have 3, maybe like we have 1 and then the 2, then you combine them. So the 1 and 2, can we also have an example like 3 or 4, and then you combine them 1?
Yes, in fact, you can have so many, but during the operation will take an input, and normally the inputs are 2. So you do
okay.
you put in 2 layers, you operate on them, and if you want to combine it again with another one, I think that would be nice. Otherwise,
okay.
to say I'm actually, yes, you can actually put in more. You can put in more if it's just combining them, but to find the intersection of 3 things, I think it's it can be done. It can be done. So it depends on the software you are using. Yeah, that's a very good question. Thank you, George. Yeah, I like contribution. So you can put 1 on top again, and then so you have 1, 2, 3. Yeah, it's possible.
So most that one will depend the software.
The software, yes.
Software that you are using.
Yes.
Okay.
Because some software, they can't do some of the things you are being told that can be done, depending on who built it. Maybe the company is not that good. They build the software, it's not working well. But of course, that's why software is so expensive, isn't it? It's supposed to do all sort of magical things for all of us. But yes, you are on point. We can have so many inputs. Yeah.
Can you touch on you made mention the component of the topology, the